Hybrid logic is an extension of modal logic that increases the expressive power of modal languages by allowing formulas to refer directly to individual possible worlds, moments in time, points in space, states of affairs, etc. It is similar to the logic of actuality. Standard modal logic allows us to talk about what is necessary or possible relative to a world, but it does not allow us to name particular worlds within the language. Similarly, temporal logic allows us to talk about, for example, what is always the case or what is sometimes the case, but it does not allow us to name particular moments in time within the language. Hybrid logic introduces special symbols that make this possible. The key idea is that we sometimes want to say things such as, this statement holds at a specific world, or at a particular moment in time, or the current world, or moment in time, is identical to a previously mentioned one. Hybrid logic provides formal tools for expressing such claims. In this way, it combines the modal perspective of reasoning about modalities with the ability to refer to individual states, or worlds, or moments in time, etc. The main motivation for hybrid logic arises from limitations in standard modal logic. In ordinary modal languages, we cannot easily express statements that refer explicitly to particular worlds, moments in time, points in space, or states of evaluation, etc. For example, we cannot naturally say that a formula holds at exactly one specific world, or moment in time, or compare the current world with another explicitly mentioned one. These limitations become important in fields such as computer science, linguistics, and philosophy. In computer science, modal logics are often used to describe states in computational systems, and it is often useful to refer to particular states directly. In linguistics and philosophical semantics, hybrid logic provides tools for modeling indexical expressions and reference to contexts. In ordinary tense logic, we can easily formalize the sentence, "It is raining," but not the sentence, "At 5 o'clock January 1st, 2026, it is raining." In hybrid tense logic, we can symbolize sentences that speak about what is true at particular moments in time. Hybrid logic therefore enriches modal logic while retaining much of its original structure and intuitive interpretation. Hybrid logic typically extends the syntax of some kind of propositional modal logic. As in ordinary modal logic, formulas are constructed from propositional variables using standard logical connectives such as negation, conjunction, etc., together with modal operators such as the box, necessarily, and the diamond, possibly. Hybrid logic often adds several new kinds of expressions, nominals, satisfaction operators, and binders. These additions make it possible to refer explicitly to particular worlds or moments in time, etc., and to manipulate references to worlds or moments in time within formulas. A central innovation of hybrid logic is the introduction of nominals. Nominals are special propositional symbols that are true at exactly one world, moment in time, point in space, or state in a model. They can therefore be interpreted as names for individual worlds, etc. For example, if I is a nominal, then in a modal hybrid logic it is true at one specific world and false at all others. This allows us to talk about that world directly within the language. Nominals thus function somewhat like constants that refer to particular states of evaluation. This feature greatly increases the expressive power of the logic while preserving the general modal framework. Hybrid logic also introduces satisfaction operators, usually written in the form at I, B. This expression is read as B is true at the world, or the moment in time, or ... named by I. The idea is that the operator temporarily shifts evaluation from the current world to the world designated by the nominal I, or from the current moment in time to the moment in time designated by I, or ... This allows us to make statements about other worlds, moments in time, etc. without leaving the current context. For example, in a hybrid tense logic, a formula such as at I box B says that at the moment in time named I, the formula B is necessary. Hybrid logics often include binders, which allow the language to introduce temporary names for worlds, moments in time, etc. One common binder is the down arrow binder, written as down arrow followed by I, and it can be read as let I name the current world or moment in time or point, Roughly speaking, the formula down arrow, IB, means that B holds when the nominal I is interpreted as naming the present point of reference, world, moment in time, ... Another important binder is sometimes called the universal binder, written as the universal quantifier followed by I. Roughly speaking, this operator allows formulas to quantify over all worlds, or moments in time or points, etc., by binding a nominal to each world or moment in time, or point in turn. In effect, it enables statements about every possible state in the model. Binders thus provide a way to simulate limited forms of quantification over worlds, moments in time, points, states, and so on within the modal framework. Hybrid logic is often interpreted using possible world semantics, similar to that used in, for example, standard modal logic and temporal logic. A model consists of a set of worlds, moments in time, or states together with an accessibility relation describing how these entities are related, and an interpretation function. The interpretation function assigns each nominal to exactly one world, moment in time, point, or state. This assignment ensures that nominals behave as names. We shall say that the model M' is an I variant of the model M if M' agrees with M on all nominals save possibly I. The truth conditions for the new expressions can be described informally as follows. A nominal is true exactly at the world, or moment in time, or point, or state it names. A satisfaction statement at IB is true at a point of reference, a world, a moment in time, ... if and only if the formula B is true at the point of reference, world, moment in time, ... named by I. A sentence of the form down arrow, IB, is true at a point of reference if and only if B is true when I is interpreted as naming that point of reference. In other words, down arrow I, B, is true at a point of reference W in the model M if and only if B is true in M', where M' is the I variant of M, where I refers to W. A sentence of the form for all I, B, is true at a point of reference, W, in the model M, if and only if, for any I variant M' of M, B is true at W in M'. These clauses extend the usual modal truth conditions while preserving the general structure of modal semantics. Logical consequence in hybrid logic is defined in the same general way as in modal logic. A formula is valid if and only if it is true at every point of reference, world, moment in time, state, ... in every model satisfying the semantic conditions of the system. Because hybrid logic allows direct reference to worlds, moments in time, etc., the set of valid formulas can differ from that of ordinary modal logic. In particular, hybrid languages can express properties of models that standard modal languages cannot capture. Several proof systems have been developed for hybrid logic. These include Hilbert-style axiom systems, which extend modal axioms with rules governing nominals and satisfaction operators, sequent calculi, which incorporate labeled formulas referring explicitly to worlds, tableau systems, where branches represent possible configurations of worlds, and assignments to nominals. Many of these proof methods build on techniques already developed for modal logic, but add rules reflecting the special behavior of nominals and binders. Hybrid logic is often constructed as an extension of standard modal logic, meaning that it preserves the usual modal operators while adding new, expressive resources. It can also be combined with other logical frameworks. For example, hybrid logic has been extended with temporal operators, epistemic operators, and dynamic operators used in, for example, computer science. Predicate versions of hybrid logic allow quantification over individuals while retaining the ability to refer to specific worlds. These extensions make hybrid logic useful for modeling complex systems involving, for example, time, knowledge, or computation. Many systems of hybrid logic have well-studied metalogical properties. For several important fragments, the logic is sound and complete with respect to its relational semantics. Some hybrid logics also enjoy properties such as decidability and the finite model property, although these properties may fail when powerful binders are added. Because hybrid logic extends modal logic in a controlled way, many techniques from modal proof theory and model theory can be adapted to analyze its systems. An interesting feature of hybrid logic is its close relationship to first-order logic with equality. The ability to name worlds, moments in time, etc., using nominals and to bind them with operators gives hybrid logic expressive capabilities similar to certain fragments of first-order logic. In fact, many hybrid languages correspond closely to fragments of first-order logic interpreted over relational structures. It is often possible to find systematic translations from hybrid logic into predicate logic with identity, and vice versa. Hybrid logic can therefore be viewed as a bridge between modal logic and first-order logic. It extends modal logic with a limited form of quantification over worlds while retaining much of its modal structure. Hybrid logic enriches modal logic by introducing mechanisms for referring directly to particular worlds, moments in time, points in space, states, and so on. Through the use of nominals, satisfaction operators, and binders, it allows precise reasoning about the structure of possible worlds models, temporal structures, etc. At the same time, it remains closely connected to traditional modal logic and to fragments of first-order logic. For these reasons, hybrid logic has become an important tool in philosophical logic, linguistics, theoretical computer science, and other fields.